If the tests from last time graded and entered, if you want to check, they're in. So if you care, you can check at your leisure. They're pretty good. You guys did pretty good. I didn't compute the average off of it, but I bet high 80s are it. So you know, so it's pretty good. So you guys seem pretty well prepared, which is great. Yeah.
Was there a curve?
No. All right. Next up, we're going to be talking about probability. This, in my experience, tends to be unnecessarily difficult for students, mostly because of like our ability to read and like understand what's happening. Like none of the computation we're going to do here is going to be worse than like multiplying and adding or subtracting. Like that's it. Those are the operations you're working with. There's no like complicated algebra happening. But you gotta understand what you're reading, which is the hard part, in my experience, for students. Everybody cool? All right. So let's start rocking and rolling here. So when we talk about probability, here's the idea. You know, like some chance behaviors, unpredictable in the short term, right? If I flip a coin and ask you heads or tails, hard to guess what the outcome's going to be, right? But if I flipped a coin 100,000 times and I asked you how many heads I'm going to have after the end of 100,000 flips, you probably be able to give me a pretty good guess and be reasonably close to being correct, right? So that's the idea for the law of large numbers, is that over the short term, over a small sample size, really hard to predict what's going to happen. But if we extend that out, if we look long enough, over enough instances, that random behavior starts to become predictable. So this is a graph that shows the proportion of heads to tails in a toss of a coin. And you see that, like, in the beginning, that proportion can kind of go haywire, bouncing all over the place. But over time, boy, that settles down to pretty close to 50-50, right? As we would expect. You guys feel good with what we're talking about here? This is just the law of large numbers, is kind of what we're talking about. That if you have a chance outcome, short term, unpredictable. Long term tends to behave pretty nicely. So we can define the term probability. So we say the probability of any outcome is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. On a test or a quiz, if the question asks for a probability and you give me a number greater than 1, you will receive 0 credit for the problem. That's an insane answer. If you give me a number less than 0, you'll receive 0 credit for the problem. That's an insane answer. If you give me a percentage greater than 100 as your probability, perfectly reasonable way to answer it as a percentage, but not greater than 100. Again, insane answer, 0 credit. If you give me a negative percentage, unless there's some like real specific reason why we're talking negative, if it's a probability, there's no reason to have a negative percentage. Again, 0 credit, that's an insane person's answer. Is everybody okay? I just want to be real clear about the expectation here. Like, it's okay for you to be wrong, and I'm happy to sign partial credit, but you can't give me an insane answer on the blank. Like, I'd rather you just write down the work and then write me, and I'll be like, something is wrong because I'm getting insane answers here, but this is what I think I should be doing. But I'm not going to put down an insane answer on the blank because I know that I won't get any credit for that. I'd rather see that note. That tells me at least that you understand, like, the kind of answer you should be expecting is not what you're getting. And you know better than to, like, say this is my answer. That you're like, I don't know, I tried doing this, but it's not working. It's okay. I'd rather see that. You guys get what I'm saying? Okay. All right. So misconceptions about how randomness works. The first one is called the myth of short-run regularity. That's the idea of probability. That randomness is predictable in the long run. Your intuition is going to try to fool you that should also be predictable in the short run. But it's not. So example, we're playing a gambling game, right? I flip a coin, you guess head or tails. If you get it right, I give you $1. If you get it wrong, you give me $1 back. We flip the coin, it's been heads 10 times in a row. It's been heads 10 times in a row. You're like, I'm going to bet $100 the next one's going to be tails. Because it's been heads 10 times in a row. Tails has got to be due. No, man. Probability has not changed. Just because it's been heads 10 times in a row doesn't mean it's any less likely to be heads this time around. It's still just as likely to be heads again. Yeah. Kevin's squinting at me. He's like, I'm not sure I believe that. That is the case. The second one is the law of averages. Tells us that random behavior evens out in the long run, i.e. future outcomes are not affected by past behavior. Idea here. You're a baseball player. You're a 10-year veteran, been a career 270 hitter. This year you're hitting 350 in the midway of the season. Expect to be a 350 hitter for the rest of the season? You should not. You're really a 270 hitter. You just had a nice sample where like things have gone your way. I would expect you to regress back to who you actually are in the second half of the season. Does that feel okay there? Again, the past outcomes not changing who you are. All right. So the core to being able to do probability is to be able to count. And we don't want to count like one at a time. We want to be able to count systematically, like how many different ways something can happen. Right? Because in the end, that's what a probability is. Like the number of ways you get the outcome you want divided by the total number of ways that the thing can happen. Everybody's okay? So like if you're at home and you're looking in your closet and you have a really sad closet and you have 2 pairs of shoes and 3 pair of pants and 4 shirts, like how many outfits can I make out of this? So that's the kind of like counting that we want to talk about, right? So, oops, that was needed to go back. Oh, back. There we go. So a little bit of vocab before we start building out how we're going to go about doing this. So when we talk about an outcome, that's a result of a try. One result, one outcome. Okay? The sample space is the set of all possible outcomes. We want to describe our trial via some probability model. To do that, we need the sample space, all possible outcomes. And we need a probability for each possible outcome. So for example, if we're talking about rolling dice, let's start with one die. Okay? What is our sample space for rolling one die? So there's 6 things in our sample space, but our sample space consists of the roll 1, 2, 3, 4, 5, and 6, because those are the 6 possible sides on our die. So there's 6 outcomes, right? Everybody's okay? There's 6 total outcomes, but the sample space is the numbers 1, 2, 3, all the way out to 6. Everybody agree? And we also need a probability to go with each one of those. What's the probability of rolling a 1? 1 in 6. Of the 2? 1 in 6. Of 3? And so on and so forth, right? They're all 1 in 6, assuming that you have a fair die, right? That your die isn't weighted one side versus the other. Everybody good? Okay. So let's look at building a probability model of rolling 2 fair die. What is the sample space going to be for 2 die?
Wait, what's the question?
The sample space for rolling 2 die.
1,
No. 2 is the lowest roll you can get with 2 dice. Right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's your sample space, right? Those are the possible rolls you can get. I know I said 6. How about the probability? What's the probability of rolling, say, a 1? Or I'm sorry, that's a 0. What probability of rolling a 2? Not 1 in 12.
136.
1 in 36. Somebody's been to the craps table. 1 in 36. Why 36? Let's look. These are all the possible rolls you could get. How many possible rolls are there? 36. How many ways did we get a 2? Just once. Right? Just once. How many different ways did it? What's the probability of getting a 3? 2 in 36, because there's 2 ways of getting a 3. Here and here. How about the probability of getting a 4? 3 in 36. There's 1, 2, 3 ways of rolling a 4. Does everybody see what's going on here? So 36 outcomes, each outcome equally likely at 1/3, but some of these events, like rolling a 3, can occur more than one way, right? They have more than one possible outcome. So we say an event is a collection of outcomes. So like before, a outcome could be rolling a 2 on the red die and rolling a 1 on the white or the blue die or whatever color that is, right? That's a single outcome. Our event would be rolling a 3. That contains 2 outcomes. Everybody's okay with the vocabulary? So again, sometimes your event is a single outcome, like rolling a 2, just 1 outcome. If your event is rolling a 7, there's 6 outcomes, right? 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. Emerson.
Should we know this off the top of our head?
The vocabulary?
Well, no. Like, you know how you're saying, like, how many, what's the chances, like, 136, like,
For rolling dice? No. No. But like if I asked you to fill out like a table of possible outcomes and then use that to find the probability, then yes, I would expect you to be able to do that. But I would like lead you along the way with some breadcrumbs. It would not be like, you need to memorize all the probabilities for rolling dice. No. Unless you plan to be a professional gambler, and then you should. So an event is a collection of outcomes from some chance process. We just looked at an example of that, right? Difference between an event and an outcome. Everybody's good? So if we typically name events with a capital letter A. So if we want P of A, that's the probability of event A occurring. Okay, so if our event is rolling a 7, we roll the 2 die, P of A would be 6 out of 36, or reduce it down to 1/6. So if our event is the sum of the rolls is 5, what would the probability for that event? The sum of the rolls is 5. Who sees that? What's the probability for the sum of the roll is 5? 4 and 36. So we have 4 and 1, 3 and 2, 2 and 3, 1 and 4. They're on a diagonal, which is nice, the way we were organized. So 4 and 36, or you could reduce that down to 1/9. Do you need to reduce? No. You can leave it as a fraction. That's totally fine. That being said, should your fraction ever be negative? No. Should your fraction ever be improper? No. Improper meaning that it's greater than 1. Can your fraction be 0? Yes. 0 is fine, right? The probability of rolling a 12, or I'm sorry, of rolling a 13 is 0. Can't happen, right? That's okay. Let's now look at a new example. What if suppose the event is defined as the sum is not 5. So how many ways are there to roll something that's not a 5? 32 out of 36. How'd you get that so fast, Olivia? Great. Yeah, 36 out of 36 minus 4 out of 36. Everything except for those 5. That's great. You've stumbled across a rule for probabilities. This is called the complement rule. So if you want to find the probability that something does not happen, you can just do 1 minus the probability that it does happen. Oftentimes, that's going to be much easier to calculate than not. Some notation for you. Oops. Yes, Brooks.
Is this sort of like factorials, like all the different ways you can arrange something?
It is a part of counting that we'll get to eventually. Yes. Quinn. Yeah. So the probability of not A is equal to 1 minus the probability of A. And that's going to occur somewhere in this PowerPoint or the next one. That'll be written down formally somewhere, but like, we just saw it, hey, let's talk about it, right? You know, like, we just discovered something intuitively. And Olivia did it without brute force counting, which is the hope to do here, because if it was like, what if we're rolling 100 dice? Oh my God, Mr. Kool-Aid, don't tell me that's something that could happen. No, I wouldn't give you that, but like, you should be able to do it. We'll talk about how to count it. All right, so these events are a set of outcomes, right? If we're going to be talking about sets, we need to talk about the notation we use to describe sets or relationships between sets. So when we write a set, we use the curly brackets, and we can enumerate, meaning we can list the elements of the set inside those curly brackets. A set has no repeated elements. Okay? No repeats inside of our set. On a test or a quiz, if I ask you to, say, blah, 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 the set this, what is this set? If you don't have the curly brackets, it's a deduction. If you repeat a value inside of your set, that is a deduction. Okay? Sets have, we're listing the set, they start and end with a bracket, no repeats inside. The notation N of A, where A is a set, just means the number of things in that set. Now there's a fancy math term for this. It's called the cardinality of the set, but that's what N of A means. It's the number of things in that set. So if we went back to the sum of the two dice is 5, if A is the sum of the two dice is 5, N of A was 4, because there were 4 ways that we could get 5 when we added up. It was okay? 1 and 4, 2 and 3, 3 and 2, 4 and 1 were the 4. The capital letter U stands for the universal set. That's the same thing as, in our case, the sample space. That's the set of everything being considered. The letter O with the slash through it is the empty set. That's a set that contains no elements. You could also write that as curly bracket with nothing inside of it. That's acceptable as well.
When would we use that? What would we be given that empty set?
If A is rolling a 13. If I asked you what A is equal to, list the event, the element or the outcomes in A as a set, you would just write an empty set. Does that make sense? Okay. This guy that looks like kind of like the letter E, but curved, just means an element in. So if we were talking about our set being sum is equal to 5, an element in there is 1 on the first die and 4 on the second die. We would say is an element, so we use that little E thing, of the set A. Everybody's okay? And when we do that, we put the outcome here and the event there, right? So it's kind of like an inequality thing. The little thing, the single outcome goes on this end, and the thing that contains it, the event, goes on that end, just like the alligator mouth for an inequality. Is everybody okay with that? Okay. If I put a slash through that element symbol, it just means it's not a member of. So again, if A is our event that the dice sum to 5, 1, 6 is not a member of the set A. Okay? It is 1 and 6 sum to 7. This symbol here that kind of looks like an upside down U is called the cap symbol, C-A-P. That means the intersection. So that intersection of two sets is the elements in common to both sets.
Wait, so when you use the Venn diagram,
That's the intersection is the overlap.
okay, so it would only be that small section.
Correct. Yes, we'll talk about Venn diagrams here shortly. I know, I'm excited too. I love Venn diagrams. No. The symbol that looks like a U with no tail, that's the union symbol. You take the union of two sets. That is everything that's in common to either set or both. Okay? So if one set is the numbers 1, 2, 3, and the other set is the numbers 3, 4, 5, the union of those two sets is 1, 2, 3, 4, 5. Notice that I did not list 3 twice, even though it was a member of both sets, because there's no repeats in sets. Everybody's okay? And then our last symbol is this sideways U. That means there is the subset of. So for example, if I have the numbers 1, 2, 3 as one set, and I have the numbers 1, 2, 3, 4 as a second set, 1, 2, 3 is a subset of 1, 2, 3, 4, because all the elements in the first set are contained in the elements of the second set. So again, that's like an operator. It goes in between two sets. Just like union and intersection are operators between two sets. Element of is between an element and a set. Or in our case, like an outcome and an event. Intersection, union, and subset are between two sets, or in our case, two events. Everybody's okay? All right. So, one of the best ways to visualize your sets is with something called a Venn diagram. Get ready, Emerson. Here we go. So, when you draw a Venn diagram, you start by drawing a rectangle. That rectangle represents the universal set. Inside of that universal set, you'll draw circles to represent your other sets. Inside of this universal set, we've drawn the set A. That's the white circle. All the stuff in the universal set that's not in A is the stuff colored green. The stuff that's not A, we call the complement of A. And the notation that we'll use is we put a little A with the little prime symbol on it, like an apostrophe on it. That means not A. There's other notations that could be used in other classes. That's the one we're going to use here. Everybody's okay? Let's look at this second Venn diagram. So we have some universal set. We called that S. That's why I wrote the S in the corner there of that rectangle. I have a set A and a second set B. Notice that there is no overlap in the way I've drawn set A and set B, meaning that their intersection is what set? Is there anything in the intersection? It's the empty set. So you could write it as the O with the slash through it, or bracket, bracket with nothing inside. Not zero inside, not the empty set symbol inside, but nothing. When we say two sets have nothing in common, i.e. that their intersection is empty, we call those two sets mutually exclusive, or we could call them disjoint. You could use those two terms interchangeably. So those three statements all mean the same thing. The intersection is empty, the events are mutually exclusive, or the sets are mutually exclusive, or the sets are disjoint. All mean the same thing. You use those three terms interchangeably. Is everybody okay so far? I'm trying to really hammer the vocab here, guys, because the arithmetic is not difficult, but like the vocab tells you what to do, and if you don't know the vocab, you kind of suck. Okay, so for visualizing two sets, A and B, if I want to talk about the intersection of those two sets, i.e., if A and B are events, we're talking about probability, the stuff in common with A and stuff in common with B would be the outcomes in both events. That is the shaded green area. That is what the intersection is. The union of A and B is everything in A and then everything in B, including the intersection, but only counting the intersection once. Because it's a set, and we are in the set, there are no repeats. Is everybody so far so good? Is this going okay? Understandable? I'm trying to like really talk through this stuff and take my time and be kind of purposeful.
No repeats.
Correct. There's no repeats ever in a set. But the union is the place where you're most likely to make a mistake.
Yeah. What do you mean by repeats?
So if A contains the numbers 1, 2, 3, and B contains the numbers 3, 4, 5, the union of A and B would be the numbers 1, 2, 3, 4, 5. We don't list 3 twice, even though it was in A and also in B. It only gets listed once. That's what I mean by no repeats. Does that make sense? Okay. Okay, and then I have my little suggestion here. You can remember the union symbol looks like the letter U for union, and the intersection symbol looks like the letter N in intersection. Maybe you need that, maybe you don't. You know, whatever. It's like one symbol, but get over it, guys. You can memorize one symbol. All right. So let's look at some example here. So let's say we flip a coin twice, or you could think about flipping 2 coins 1 time each. It's the same idea. If we want to record the results to represent the sample space, what would the sample space be? How many outcomes can we get from flipping a coin twice? That's incorrect. That's incorrect. 4 is correct. What are the 4 outcomes?
Heads, tails, heads, heads.
Correct. So those are the 4 outcomes that Anthony's described. And if I was going to list that then as a set, remember we need curly brackets to go around it. If you forget your curly brackets on a test or a quiz, it's going to earn yourself a deduction, just like if you don't 3 sig fig it. You know, we've all been there and been like, oh, Mr. Kulik, you're such a sig fig jerk. I'm like, well, it's not that hard. We've been talking about it the whole year. You haven't figured it out yet, guys. Okay. Everybody feel okay with what we did there? So, the U, again, why did I use the letter U there? Because U stands for the universal set. That's the set of all possible outcomes. That's half of our probability model. What else do we need to go with our probability model other than the universal set or sample space? What else do we need for a probability model? You don't need a Venn diagram. We don't need a union. We need the probability of each of those 4 outcomes. What's the probability of HH? 1 in 4. The probability of HT? 1 in 4. The probability of TH? 1 in 4. The probability of TT?
What if one?
1 and 4. Everybody feel good on that?
Mr. Coleman is restroom.
Yes. So this is the same thing we just listed in a table. Who cares? What if we want to do this as a tree diagram? Oftentimes this is a helpful way to envision a problem that's maybe a little bit more complicated than this one. So in our tree diagram, basically we have a branch for each kind of an outcome. So when we toss the coin the first time, we have 2 outcomes, heads or tails. After we get a heads, we toss the second coin, we have 2 outcomes, head or tails. Or if we've gotten tails, there's 2 outcomes, head or tails. So there are 4 possible outcomes here. The first outcome, if I follow the first branch, is HH. The second outcome would be HT. The next one would be TH. And the last one would be TT. Just by following the branches. Did you guys see how I got to that? Again, this tree diagram construction will be something that we will use to do some probability computations. It is a really handy visual way of representing what's going on and makes a lot of these computations a lot simpler if you visualize it. Okay. What if we did this as a Venn diagram? What would it look like to represent the sample space in the Venn diagram? I mean, it's like the dumbest Venn diagram ever, right? Just the sample space is everything that's in there. So you don't even need a circle. You just write the rectangle. 4 things in your rectangle if you want to do that. That's fine. How about as a probability table? So here, notice that I've represented the tosses as ordered pairs. First toss, comma, second toss. Everybody's okay with that? This is all doing the same thing, right? I'm just conveying you the same set of information like 4 or 5 different ways. Because guess what? Are you going to get the information the same way every time on a quiz or a test or homework? No, you won't.
Oh, it's a.
Oh, Mr. Kruick. All right. Let's look at some more examples. When rolling a standard 6-sided die, what is the set of event A, where event A is observe an odd number? You're rolling a standard 6-sided die. Event A is observe an odd number. What is the set for event A? Who can do this? You all should be able to do this. It's quite easy. 1, 3, 5.
1, 3, 5. 1, 3, 5.
But again, remember, what do you need to make sure you have?
Brackets.
Brackets.
Oh, screen gets deducted.
And make sure they're all inclusive.
No. That was no.
These are exact values. You probably
These are
don't.
exact values and not exact.
You don't need to real.
That's really embarrassing. Okay.
You observe a number less than 5.
Oh.
What is that set?
Probably 1. It's either 1 or 3. So 2/3.
So it's an event. So it's a set.
1, 2, 3.
1, 2, 3, 4.
But it's square.
Those are the values. Those are the numbers less than 5. What about the event A intersect B? Okay. So it's the set 1 and 3. So you could visualize it with a Venn diagram. Or you could just look at the values that are included in both sets, since we did already sets A and B. How about not A? What is the set not A?
Just B.
246 is correct. Don't fail this quiz.
Wait, you're the quiz?
No, not right now. I mean, yes, but not like imminently. It's the first day we're doing it. What about, now we're getting complicated, A union, not B?
One. No, no.
2 and 6.
2, 4, and 7.
1, 3, 5, 6 is correct. I heard.
Wow. Okay.
So again, let's look at what we have. A is 1, 2, or 1, 3, 5. Not B is 5 and 6. The union of those two is going to be 1, 3, 5, 6. You see it?
Yeah.
Again, nothing we're doing is tremendously complicated yet. There's been a lot of vocabulary. There's been a lot of symbols. But like, what are we doing here? We're just like looking at a picture and saying what stuff is, right? Now, the ability to do that requires that you know the symbols and you know the vocabulary. But once you know those things, doing this is like trivially easy to you can do it in your head, right? Hope so. Using words, interpret event E. Tell me in words, what is event E? Oh man, that's a bonkers
How did
answer.
you come up with that? Oh, it means, it's A but not B. A not B.
So it's observe an odd number or observe a number not less than 5. Again, if we're doing it in words, it needs to be referred back to the specific situation. So just writing A or not B is not sufficient. We have to say what A and B are in the context of the problem. Here we're talking about rolling a dice, right? Is everybody okay with what we just did there? Okay. Here's some basic set rules that are probably pretty useful. The intersection of A and B is the same as the intersection of B and A. It's commutative, just like addition. Everybody's okay? Same thing works for unions. The complement of the complement is just A, right? I'm not interested, right? Means that you're interested. A union the universal is the universal, that's right. Oh, I was the intersection though, I said the wrong symbol. You answered the question I said, and read the wrong thing. A intersect the universal is just A, because the overlap between them is just going to be A, right? Because the universal is everything. The union of A and the universal is the universal because it's either place, and then the universal is everything, so it's just everything. Now, I want to point out to you that this relationship here with A and the universal will still hold if U is any set containing A. Even if it's not the universal set. If A is a subset of U, that same thing holds, right? Because all of A is in the universal, or all of A is in the superset. The same thing would hold, even if that set was B and not the universal. If it contains all of A, the same relationship. What's the intersection of A and not A? What do they have in common? Nothing is the correct answer. Yes. The empty set. What's in common between A and not A? Well, nothing, right? What's in common between the even numbers and not the even numbers? Nothing, right? How about the union of A and not A? Yes, that's going to be the universal, right? If you take everything that's not A and A and you put them together, that's everything. All right, 2 more properties. These are called De Morgan's laws. So the A union B, if I want the complement of A union B, what do you think it is? Yeah, Anthony's seen this before. Not A union, intersect, not B. Not A intersect, not B.
Minus the intersect.
So if you draw the picture, here's A and B, and it's not A and B, right? So it's that part of it. You agree that that's that? So here's A, here's not A, here's B, here's not B. What was the overlap between them? It's just the exterior of the circles, right? Does that make sense as to why that they're still equal? Okay. What about A intersect B complement? The complement of A intersect B. What do you think that's going to be? Not A or not B. So again, you're seeing the same flippy floppy, right? So the way you should remember it is when you distribute the not, it flips unions and intersections. That's the way I remember it. Okay. 2 tetrahedral dice with sides numbered 1 to 4. One is blue and one is yellow, are rolled. List the elements of the following events. The first event is T, and it's the set at least one dice lands on 3. Quinn. Sure. So I would start by writing out the full sample space, right? So that should be my T, right? Are those 7 outcomes? You guys agree? See what I did? Just kind of built a table to represent what was going on. So there's the same table. That's what the book built. That's exactly what we just built ourselves, right? Was it? Oh, dice lands at least, lands on 3. Excuse me. So we want that stuff, right? I thought it was 4. My mistake. Still 7 outcomes, though. Everybody's good? So there we go. That's my T. Again, do we do anything massively complicated here? No, man, we just kind of like drew a picture and described what we got, right? How about the blue dice lands on 3? Yeah, just 4 of them, and those are the 4, right? Where the blue die column is 3. How about the sum of the dice is 6? I see just 3 of them. 2, 4, 3, 3, 4, 2. And that's the end of our thingamajigger. I'm going to not save any of these notations, just so you, like the little tables that I drew extra. All right. 8.1 examples. Get your little thinking caps on. I'm going to call on people randomly. You don't get a choice today.
Call on Lucas. No, you don't.
I will if I so deem it. All right. The first question says, suppose that exactly 5% of a specific type of cell phone under warranty will be returned and the cost to replace them is $150. If the manufacturer knew which phones would go bad, they could just charge a $150 warranty for those phones and $0 for the rest. However, the manufacturer cannot know which phones will need to be replaced. If the manufacturer wishes to be as fair as possible, how much should the manufacturer charge every customer for the warranty? All right, let's see. Who am I going to call on? Sam, what do you got?
What's 5% of 150?
That would be the answer, wouldn't it? That's correct.
75. Or no.
750, I think.
Yeah.
Why?
Because it's 5% of the phones that are malfunctioning, and the cost to replace it is also 50.
Yeah, so the other 95% of the phones get charged $0, right? Do that, $750 per phone for everybody. What did we just basically do here? We've done this already. This is just like our weighted average. Remember, we have this frequency diagram or the frequency chart and the values, and we have to calculate an average with the frequency. That is essentially all we've done here. This is a fancy statistics name. This is called expectation, or expected value. If you're a gambler, this is like what it's about. Because if the probability that you win times the amount you win is greater than it costs to play the game, you play that game as much as you possibly can. If you go to a casino, all of the games cost more than their expected value. They are set up for you to lose over the long term. That's how casinos never go out of business unless you're Donald Trump. He managed to bankrupt 2 separate casinos. He's not the only one who done that, by the way. That's a good question. I'm not really sure the exact reasons. I think it has more to do with like the rest of your finances. But anyways, continuing on. A die is rolled 12 times and we record the result of each roll. Which of the following outcomes is more probable? Well, Emerson, I guess I'll call on you since you went ahead and blurted it out. Why do you say the second one?
Because I feel like in the second one,
There's less repeats.
they're the same numbers.
They are the same numbers, just different order. That's correct, Colby. So it is a trick question, Lucy. Very good. Why is it a trick question?
It's the same.
They are the same. Because does order matter? No. Is the probability of rolling 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 still the same as these ones? Yup. Does it look like that would be very likely to happen? No, but it's the same as like if they appear, the same sets of numbers appear in a random, like in a random appearing order, still the same. This is one of the best ways that we have to detect people that make up data. Because they try to make the data look too random, and actual random data isn't that random looking. So people that cheat and make stuff up, make up numbers, make up data, you can often tell just by like the distribution of the numbers they choose. Isn't that neat? So they had I can't remember, I think it was in Atlanta, they had like a school where they were like systematically cheating on the standardized tests, like the teachers were changing responses or whatever. And like this is kind of one of the ways they detected it, was like looking at the result. Anyway. In casinos, there's often a large display next to every roulette table showing the outcomes of the previous spins of the wheel. The results of previous spins have no effect on the results of future spins. So why do casinos use these displays?
To trick people.
To trick you into gambling, thinking the odds are better than they actually are. That's exactly what they're doing. That's how casinos stay in business, by tricking you out of your money. They don't stay in business by helping you out at all. Give the probability model for flipping a fair coin 3 times. Who can do this? All right, I'll call on somebody then. Jamie.
Hi, from a friend.
You can't even start it?
No, it's flipping. Wait, were we on number 4?
Yes.
See, that's like a map. Can you just can't you just,
Okay.
wait, and, yeah, can't you just flip the coin, like, what, oh, the bracket. Oh,
So
two
it's,
sides.
so you have to have a sample space to start.
Wouldn't it just be like heads, tails,
Heads, tails,
heads,
that's one possible outcome.
or you could have heads, tails, tails. Or you could have like tails. Look at my head. Or you could, did I say all of them?
Yeah.
Okay. Or you could have it tails, tails, tails. Or you could have heads, heads, heads. Or on the same one. You could have HHT. TTH.
Well, I'm sorry, two people said stuff at the same
Oh,
time.
TTH.
We did HHH.
And then you have.
We have THD. We have H, what? We have T. We have TTH. Are we missing any?
Yes.
Yes. THH. How do we know how many should be here? How many choices do I have for the first coin? Two. How many for the second coin? How many for the third coin? Two times two is 8 possible outcomes. Do I have 8 on my list? Okay. Now, what else do we need for a probability model? We have the sample space. That's one half of it. What's the other half? I need the probability for each event in the sample space. Good. Nicole, what's the probability for the HTH? 1 out of 8. So we're just going to write it this. I'm just going to write that way. It's 1/8 for every outcome in N, in S. Sound good? Okay. U is the universal, or I'm sorry, the universal set is all the integers from 1 to 10 inclusive. A is the even numbers between 1 and 10 inclusive. And B is the set 2, 3, 5, 7. Ella, help me build a Venn diagram for this situation. What do I start by doing? Draw a rectangle. Thanks, Ella. It's okay. And then I put a U in the corner to say that represents the universal.
And then the 2 circles.
So the 2 circles, and label them A and B.
Yeah, let's do
Okay.
3.
Where am I putting the 3?
Only B.
Okay.
Oh wait, all integers. Yes. 5 as well, and 7 and 2. 2 in the middle. Okay, I'll leave that from here. And then in A there'd be 4.
You mean just A?
Just A. 4, 6, 8, 10.
Are you done?
About 1. Outside
Yeah,
of it all,
1.
the universal is all the integers. Oh.
All, I'm going to be writing a long time if you want me to write all the integers.
I mean, and not. You just do 1 through 10.
That is what it says.
got one. You got one on A.
No.
Outside. Outside. And the U.
Are we done now?
Yes, I think so.
Nope.
D9.
Nine. Come on now. And then 9 would also be on the outside.
Now we're done.
Now you're done. Very good. Is everybody okay?
Can I go to the
All right. We're shading. Anthony, how do I shade this for not A? Outside of the box?
Oh! No, Jagrani said outside the box, and I was trying to correct him. Not
No, he didn't.
outside of the circles, inside the box. And then inside of B, that's not the box.
Everybody agree? That's correct. I'm going to erase because we have to do this again. And it's going to get like so disgustingly muddled after 5 of these things that nobody will really tell what's going on. All right. Olivia, B.
Everything is outside of the circles, inside.
Everything outside the circles, but still inside the box. I like how you added in still inside the box, because you knew I was going to go
Thank you.
and just start coloring the whole paper.
Yeah.
That's correct. Is everybody okay? Feel good on that one? Okay. Let's see. Henry, can you do C for us?
Let's go, Henry.
A intersect, not B. Okay, let's do it in 2 pieces then. Let's shade just A. How would I shade just A? Okay. And then let's shade not B.
Like the other, the circle without B. Like, you know what I'm saying? Yes, that, yeah.
But it also has this stuff too, right?
Yeah.
Okay. And what is the overlap between the red and, or the green and the blue? Because we're doing intersection. It's that part. That is our answer. So if it's too confusing the way it's written, because there's a lot going on there, draw them as 2 separate and then look for the intersection, look for the union. Right? Draw each set separate and then look for the union or intersection. Does that make sense? Okay. I'm erasing. Here we go. All right. D, Jacob.
We're gonna do the stuff around both circles and inside the box, and then like all in circle B, stuff out of that.
Everybody okay with that? So the not A covered all of this stuff, right? And then the B covered this stuff. And because it's a union, it's both of those shaded parts, which is what Jacob described. Good job. And E, Brooks.
Would it just be full circles except for the intersection?
Almost.
And the outside.
And the outsides. You know why the outsides?
Because it's in the brackets, the parentheses.
Yeah, sure. Everybody's okay? Next question. There are 40 students at an IB school are studying either chemistry, biology, or both. 25 are studying chemistry, 19 are studying biology, and 4 are studying both. Represent the information above as a Venn diagram and as a two-way table. How many students are studying just chemistry? How many students are studying just biology? Okay. Colby. This one's up for you. Start by doing that. Help me fill in where things go. Which part?
The C.
But there's two places I can write it here.
That's because they overlap.
Not the overlap.
Okay.
And then 19 and D.
Okay.
In the overlap.
Okay.
4 in the overlap.
Okay. Can I first point out to you that we have a problem? If I add those up, I get 48. There's only 40 students. So that is where we should start, with the middle.
21 in chemistry.
Yeah. That gives us 25 total in chemistry now.
15 in biology.
Okay. And if I add those up, what do I get? I get 40, right? That's good. Everybody agree? Okay. Now, if I do this as a two-way table, that's what I'm going to do. So this is B and C. This is C and not B.
Yeah.
This one is B. Oh my God. Mr. Kool-Aid. B and not C. And this one is not B and not C. Is everybody okay with how I built my two-way table and used my Venn diagram to inform what I did there? Does that feel good, Cole? Okay. All right. There's 50 people in a band. The conductor wants to know who can play the saxophone, who can play the trumpet, and who can play the drums. He finds that 2 people can play all 3 instruments. 5 can play just the saxophone and the trumpet. 1 can play just the saxophone and the drums. 3 can play just the trumpet and the drums. 22 can play the trumpet. 15 can play the drums. 18 can play the saxophone. Represent the information as a Venn diagram above. Quinn, this is you. Yeah, it's going to be 3 circles. So, saxophone, trumpet, drum.
So there's 2 in the middle.
In the triple intersection.
5
That's this one.
Yeah.
Now, why didn't I have to make that 3 instead of 5?
Because he's really specific. It's just that.
Just saxophone and drum. Or trumpet. No drums. Okay.
There's one in the saxophone, 3 in the drum, trumpet.
Is that just yeah. So I'm gonna knock it up. 12
Good. Yup.
Good afternoon, Notre Dame. Before we end our day in prayer, student council juniors want to remind other juniors to remember to bring in your donations for your CT gift basket by Friday. So again, juniors, remember to bring the donations in for your CT gift basket. And now let's end this day together with a prayer for the canonization of Jean-Claude Collin. In the name of the Father, the Son, and the Holy Spirit. Amen. God our Father, your servant Father Jean-Claude Collin, inspired by Mary, our mother, founded the Society of Mary. He taught Marys to imitate Mary in their life and ministry, proclaiming Jesus Christ while preferring to be hidden and unknown in the world. They would make every effort to achieve holiness, to lead others to sanctity, and to remain loyal to the teachings of the Catholic Church. They would treat everyone, even the hardened sinner, with mercy and compassion. Father, grant blessings to your people through the intercession of Father Collin. Guide your church to declare him a saint, so that his life of gentle virtue may become an inspiration to others. We pray in the name of Jesus Christ our Lord. Amen. Notre Dame, have a great afternoon and God bless. Teachers, you may dismiss when you are ready.
You guys should be able to do the 8.1 homework. If you haven't filled out every single person's survey that's available to you currently on My Notre Dame, whether you are collecting data by survey or not, you need to do that. We're all counting on each other to get enough data to make this thing go. You must do that, whether you're collecting data via survey or not. Get them done. Thank you.
There were like 2 surveys that when I tried to open them didn't work.
I've talked to the people. They should be hopefully open by now.
Right.
I think it was Maggie and Ethan.
Something like that, yeah.
Yeah.
I was able to edit those.
You were